All right, so let's recap the story so far. Chapter 1 merely introduced the concept of a differential equation and initial value problem. And we saw some examples of where they're used, but we didn't have any techniques for solving any of those differential equations yet. In Chapter 2, we were concerned principally, in fact entirely, with first-order differential equations. And we were able to solve a whole bunch of first-order differential equations by classifying them as separable, linear, exact, or having homogeneous coefficients, or by some cool little moves that we could do to kind of reduce them to one of those categories. And then in Chapter 3, we revisited some of the models that we saw in Chapter 1, but we're now armed with the ability to solve those differential equations because of everything we learned from Chapter 2. So where does that leave us? Well, in Chapter 4, we're now going to learn how to solve second-order equations and higher. And remember, the order of a differential equation is just the highest order derivative that appears. So we're now going to see second-order derivatives and third and so on in our problems. In order to pick up the techniques that we're going to need, we're going to have to look at a bunch of new terms and processes in this section, and that's what section 4.1 is all about. So we're not actually going to be doing any solving today. We're going to be looking at sort of how solutions are constructed, what behaviors they take on, and some of the general vocabulary surrounding some of their pieces. So let's recall a very fundamental principle, and that is that the general solution of an nth order differential equation will possess n parameters. So, of course, what we've seen so far are first order differential equations, and that's why all of our general solutions always just had a c value in them. Well, for second order differential equations, the general solution will have a C1 and a C2. And for third order, they'll have a C1, a C2, and a C3, and so on. So let's quickly look at a general solution and use it to solve an initial value problem. Okay, so here we are told that this family of functions is the general solution to this third order differential equation here. Notice that preliminarily, at least, that's an acceptable claim because we have three parameters and this is a third order differential equation. We are going to use the initial values here to determine what those three parameters are, and then we'll have the particular solution to the initial value problem. We could, but we're not going to actually verify the claim that this is a general solution. We're going to take it at face value. We do know how to verify that. So it's a matter of just taking a bunch of derivatives and plugging them in and seeing that the identity here is true. So we're just going to go straight in and find the C1, C2, and C3. So what we are going to need are the first and second derivative of our general solution here so that we can actually plug values into it. So we are given that y is c1 plus c2 cosine of x plus c3 sine of x. So let's quickly find first and second derivative. First derivative would be negative c2 sine of x plus c3 cosine of x. And the second derivative be the derivative of that, of course. And now we can plug in the initial values, and what we're going to get is a system of three equations with three unknowns. So cosine of pi is, of course, -1, so that's c1 minus c2. Sine of pi is 0, so great. Okay, so we have this equation. Let's put it aside. And we know that y prime of pi is equal to 2. So that means that 2 is equal to, we'll take y prime and replace x with pi. Again, sine of pi is 0. That's lovely. So we have negative c3 because cosine of pi is negative 1. This tells us actually c3 right away is negative 2. Well, that's very nice. So y double prime of pi is equal to negative 1 was our last given condition. So we'll plug the pieces in there. C3 is negative 2, so rather than just writing C3 here, let's write negative 2 sine of pi. That wasn't particularly helpful anyway, because that term's going to disappear. And cosine of pi itself is negative 1, of course. So, all right, this tells us that C2 is negative 1. This is a pretty easy system of equations, all things considered. Since we have two of the variables already for free, we can go back to this 0 equals C1 minus C2 business and say, since 0 is C1 minus C2 and C2 is negative 1, okay, well this tells us C1 is equal to negative 1. So therefore, the solution to the IVP is the function from that family with the specific constants that we determined. So C1 being negative 1 and C2 being negative 1 as well, and C3 being negative 2. So this function satisfies the initial conditions as well as the differential equation. So we're done. Okay, we are going to see that it's going to be essential to be able to classify nth order linear differential equations as either homogeneous or non-homogeneous. Now, the term homogeneous here applies to an entire differential equation. This is in contrast to our use of homogeneous in chapter 2, where it applied to a specific term. So it's not quite the same usage, although the intent in the background is very similar. So let's define this. All right, so here we have a linear nth order differential equation. So remember what that means is, of course, the highest order of the derivative is n, and all the derivatives are of the first power, first exponent, and you just have stuff involving x times a derivative, plus stuff involving x times a derivative, all the way down, right down to stuff involving x times y to the 0th derivative, and then everything that's not multiplied by the dependent variable or its derivative is just pushed to the right-hand side and called g of x. Now, if there are no such terms, meaning g of x is 0, so the right-hand side is 0, then this equation is called homogeneous. Otherwise, it's non-homogeneous. So, for instance, this guy here is a homogeneous equation, and this guy here is non-homogeneous. And that would be because of this extra term here. So note that even something that looks homogeneous might not be. So if you have like y double prime plus 6y plus 1 equals 0, this is not homogeneous because that 1 really belongs on the right-hand side as negative 1, making this a non-homogeneous equation. One of the big reasons why this distinction is important is because the main technique we use to solve an equation like this, which is, say, non-homogeneous, is by first writing its associated homogeneous equation, that is, discarding everything on the right, and the technique for solving that is significantly more straightforward. And it turns out that the solution to the associated homogeneous equation is actually going to be part of the solution to the non-homogeneous part. Once we have that first solution to the associated homogeneous equation, which is called a complementary solution, we then put our attention towards this 3e to the x, or whatever is part of the non-homogeneous part of this, and we get something called a particular solution, and then we combine the two solutions using something called the superposition principle. And at that point, we will have the general solution to our original non-homogeneous differential equation. It's going to take us a few sections of theory to get to that point. But that is the main idea here. Okay, time for a brief notational interlude. I'm going to introduce something called the differential operator here. So it's often convenient to denote d dx with simply a capital D. So for example, instead of saying that the derivative of sine of 3x is 3 cosine of 3x, you could say d of sine 3x is 3 cosine of 3x. Or the derivative of y with respect to x, you can simply write as dy. The second derivative is d squared y. And all the pieces still work here. Like d squared would be kind of like the square of d dx being multiplied by y. So that's d squared y over dx squared. All right, and the nth derivative of y with respect to x is capital D raised to the n times y. So D is called a differential operator, and an operator is sort of a machine in mathematics that applies to functions and transforms a function to a different function, which is what we've been doing all along, taking a derivative ever since the beginning of calculus. Just transforming functions to new functions. So a linear differential equation can be easily expressed in D notation. So for example, if we have y double prime minus 6y prime plus xy equaling 3x squared, which, by the way, is non-homogeneous, we could write this as d squared y minus 6 times dy plus xy equaling 3x squared. And writing it this way allows us to factor the y out of the left-hand side. So we have something like d squared minus 6 plus x as an independent factor multiplied by y equals 3x squared. And we can think of this entire object being an operator itself that, when applied to the unknown function y, gives us 3x squared. This allows us to kind of look at that operator itself and perhaps if we could find a way to invert it and apply that inverse to 3x squared, well then we'd get the unknown function y. And that's the direction we're headed into here. All right, we're now going to see the superposition principle, which is a basic principle applying to homogeneous equations that basically tells us if you have two or more solutions to a particular homogeneous linear differential equation, then you can add them together and you'll get another solution. So let's say we have k solutions to this particular homogeneous nth order differential equation on an interval I. Then the linear combination y equals some constant times the first solution plus some constant times the second solution plus dot 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 some constant times the kth solution well, this thing here is also a solution on that interval of definition. So a linear combination of any two quantities just means some multiple of the first quantity plus some multiple of the second quantity. So for instance, 3 sine of x minus 5 cosine of x is a linear combination of sine and cosine. And what this superposition principle is saying is that if you have some list of solutions that you know are solutions, that a linear combination of those solutions is also a solution. So if we have a differential equation and we know sine of x is a solution and we know cosine of x is another solution, then this, which is a linear combination of sine and cosine, would have to be a solution to that particular differential equation, provided the differential equation were homogeneous. Let's actually write that example down formally. Okay, why don't we sketch a proof of this very important and useful theorem? We're just going to prove the case for k equal to 2. So supposing we have two solutions, we're going to prove that the sum of those solutions is also a solution. So suppose we have a linear nth order homogeneous equation. And let's write it using the d notation. So we have an of x, and instead of d to the n y dx to the n here, we're going to write this using the d notation. So d to the n of y plus d to the n minus 1 of y plus all the way down to the first derivative, including the zeroth derivative, which would just be y. And this is homogeneous, so the right-hand side is 0. There are no terms without a y factor. Okay, then of course, because of the denotation, we can see that let's factor y out and treat this whole thing as an operator on y. All right, now this operator is a perfectly good operator in its own right, so why don't we just call this whole thing L? So what we have is L applied to y equals 0. That's our differential equation. Very, very compactly written. So, all right. What we're going to do is we're going to suppose we have two solutions. We'll call the first one y1 of x, and we'll call the second one y2 of x. Okay, so what does this mean? Well, this means that if we go back to our differential equation and replace y with y1 or y with y2, then we're going to get 0, right? These actually satisfy the differential equation. L of y1 is equal to 0, and L of y2 is equal to 0. Now what we'd like to show is that because we know y1 and y2 are solutions, that any linear combination of y1 and y2 will also be a solution. So we'd like to show that c1 y1 of x plus c2 y2 of x is also a solution, with c1, c2 being arbitrary constants. In other words, we'd like to show that L of c1y1 plus c2y2 is equal to 0, meaning that if you replace y with c1y1 plus c2y2, you will still get 0 on the right-hand side. All right, well, let's take a look at this thing. So we can't say it's 0 until we can justify that it's 0 using the given information. So we're just forced to play around with this. But we know that L is linear. So differential operators are linear, meaning they distribute across terms. You learned this in Calc 1 when you learned early on that you could distribute a derivative across a sum. So we have L of c1y1 plus L of c2y2. And just like you can pull a constant out of a derivative, and indeed an integral, which is the inverse of a derivative operator, you can do that here. So we get c1 L of y1 plus c2 L of y2. All right, but we were given that L of y1 is 0 and L of y2 is 0. So what we have is c1 times 0 plus c2 times 0, which of course adds up to 0. So since L of c1y1 plus c2y2 is confirmed to equal 0, we have shown that c1y1 of x plus c2y2 of x satisfies the differential equation. Well, therefore it's a solution. So this shows the k equals 2 case, because we only applied it to 2 functions. But using a process called mathematical induction, you can extend this logic to apply to any case by simply noting that now we have a solution, and if you just added a third function, you could run through the same logic using this guy and that third function. Before going on, we're going to just write down 2 corollaries. A corollary in mathematics means a fact that follows somewhat trivially from something else that you established earlier. So one is that simply a constant multiple of a solution to a homogeneous linear differential equation is just another solution. So for example, if y equals 6e to the x is a known solution, then you can just say, well, y equals constant multiple of 6e to the x. In fact, you don't even need the 6. You can just say any constant times e to the x would have to be a solution to that particular differential equation. And another corollary is that y equals 0, it's called the trivial solution, is always a solution to a homogeneous linear differential equation. If you look at the form of a homogeneous linear differential equation, you don't even need this much machinery to convince yourself that y equals 0 is necessarily going to be a solution, because all the derivatives of y equals 0 are themselves 0. So the whole left-hand side of a homogeneous linear differential equation, we just zero out. Of course, that equals 0 on the right. So there we are. Okay, now we need to shift gears a little bit again and put our attention toward a notion of linear dependence and independence. So what does that mean? We're going to define it in just a moment, but I first want to explain why we need this and what we're really talking about. So what we just did a few minutes ago is learn that if you have 2 solutions to a homogeneous linear differential equation, that you can add them together and get a third solution. So that actually raises a new question, which is when is it relevant to do that and when is it not relevant to do that? For instance, if we have the solution 5x and we have the solution 7x, and we, for whatever reason, we know those are two solutions, is it worth us saying, oh, that means we can put together C1 times the first guy, again, the 5 getting absorbed, plus C2 times the second guy, the 7 getting absorbed into that constant. I mean, that's kind of a silly thing to write because we know, in fact, that 5x and 7x are really kind of just two different expressions of the same family of solutions, which is really just C1x, right? So let me make a more subtle argument here. Suppose we are told that 3 sine of 2x is a solution to a differential equation. And we're also told that negative cosine of x times sine of x is a solution. So again, applying the superposition principle, a person might think, okay, well then a constant times sine of 2x plus some other constant times cosine of x sine of x gives a more general family of solutions. This is true, except that sine of 2x itself is a multiple of cosine x sine x, right? We know that in fact sine of 2x is 2 sine x cosine x. So again, these two solutions are actually just different expressions of the same particular fundamental element solution, right? So what we want to do is kind of get at when can we do that and when can't we do that? When can we combine and when can't we? So in this case, we could easily just write y equals a constant times sine of 2x, and that actually covers both of those cases. However, if we had a third one, like say 6e to the x, well, we know probably, and in fact it's true, that we cannot just write 6e to the x as some kind of multiple of sine of 2x. So in this case, we would have to now add like a second guy here and say plus c2e to the x. The name of the quality that we're putting our hands on here is that sine of 2x and cosine times sine are linearly dependent, meaning one really is just dependent on the other, whereas e to the x is independent of these other ones. So there's no way to express e to the x in terms of purely sine 2x and cosine times sine. So in order for us to manageably put together these different forms we're going to see and see which ones are necessary to include in a linear combination and which ones are not, we're going to need to formally talk about linear dependence and linear independence. So let's define what those are and come up with a way that we can establish conclusively whether or not a particular set of functions falls into one category or the other. So suppose you are considering a set of functions, n of them. Well, this set of functions is called linearly dependent on the interval I if there exist constants c1, c2, all the way to cn, and not all 0, and that's essential, such that c1 f1 plus c2 f2 plus cn fn is equal to 0 for each x in the interval I. All right, so linear dependence means that if you form this particular equation, there exists some set of numbers, c1, c2, cn, and they're not all 0 that make this true. Of course, it's always true that if you set them all equal to 0, this is going to work. But you only have linear dependence if there exists some set of them where at least one of them is not 0. If there is no such set, meaning that this only occurs when C1, C2, etc. are all equal to 0, then you have a linearly independent set. So for a linearly independent set, the only way this particular identity can hold is if literally all the constants equal 0. Okay, let's look at some examples now. All right, let's revisit sine of 2x and sine x cosine x. So the claim here is that they're linearly dependent. Let's see that. So what we're going to do is we're going to go c1 times f1 plus c2 times the other one, sine x cosine x. And we'll set that equal to 0. So is it possible for c1 and c2 to exist where at least one of them is not 0 and this still hold? And again, I want to stress this will always hold with c1, c2 equaling 0. But for linearly dependent set, it must mean that there exists at least one set of constants where at least one of those constants is not 0, and then you have linear dependence. Indeed, if we have c1 equal to 1 and c2 equal to -2, then this equality holds. All right, in contrast to that, we have this example with the set e to the x and x squared. Okay, so let's check and see if these are linearly independent. So we have c1 e to the x plus c2 x squared, and we're setting that equal to 0. Is it possible to find a pair c1 and c2 where at least one of them is not 0 and make this equal to 0? And the answer is no, it's not possible. The only solution to this is if c1 equals c2 and equals 0, which means that the set is linearly independent. Okay. All right, so the next thing we're going to see is a method using matrix determinants for conclusively establishing whether or not a set of functions is linearly dependent or linearly independent. Okay, so let's get a refresher on matrix determinants. If you've taken linear algebra, you're probably very good at matrix determinants. Otherwise, the last time you saw them may well have been pre-calculus, or you may have never seen them at all. So they're pretty straightforward. So let's go over how to calculate a determinant. Okay, so let's start with a 2x2 determinant. So let's say we have a matrix A, and it's a 2x2 matrix, meaning 2 rows, 2 columns, consisting of the entries A, B, C, D. So the determinant is denoted, well, there are several ways. You could either write det A, or you could write A in sort of absolute values, where in the context of matrices, that means the determinant of A. Or you could even write out literally the terms of A, but instead of using the brackets, meaning the matrix itself, we use vertical bars, which means the determinant of A. And all of these are computed by taking the diagonal of the matrix A and multiplying those entries. So we have A times D, and subtracting the anti-diagonal product, so that would be B times C. This formula is strictly only for a 2x2 matrix determinant. For a 3x3 matrix determinant, we're going to have a formula for this, but it's not a formula that's practical to actually memorize. It's a process that's easier to understand. So if you have a 3x3 matrix, the idea is you take the first two columns and you write them here again. So we have the first column followed by the second column. And what you do is you take the first three diagonals and multiply their entries together and add the products. So we have the first diagonal, which is A times E times I, plus the second diagonal, which is B times F times G, plus the third diagonal, which is C times D times H. So these guys are each being added in to your final answer. We are only halfway done though, because then you take the three anti-diagonals and you subtract those products. So we're going to have minus G times E times C minus H times F times A minus I times D times B. And there's your formula for 3x3 determinants. There actually is a general process for finding the determinant of any n by n matrix, which is beyond the scope of this course. So you will see that if you take linear algebra. So we're only going to deal with 2x2 and 3x3 determinants, and we're going to use these shortcuts for each one. So let's calculate a couple of determinants really fast. All right, so the determinant of A, which we could write as vertical bar and then the matrix A. So for 2x2, it's very straightforward. It's just the diagonal entries, 3 times 4, minus the anti-diagonal entries. So -2 times 16. So this would be 12 plus 32, which is 44. So the determinant of that matrix is 44. Okay, let's find the determinant of the matrix 1, 0, 5, 3, 9, -1, -1, -2, 6. So for a 3x3, remember we copy down the first two columns right here. And then we multiply out of these and add those products. So we get 1 times 9 times 6 plus 0 times -1 times -1 plus 5 times 3 times -2. And then we will subtract these three. So minus -1 times 9 times 5 minus -2 times -1 times 1 minus 6 times 3 times 0. All right, so let's just work everything out. 9 times 6 is 54, plus 0, and then it looks like minus 30. And then over here we have plus 45. And then over here we have minus 2. And then again minus 0. So this would be 54 minus 30 plus 45. That would be 69 minus 2 is 67. So our determinant is 67. All right, in this course, we're actually not going to be taking determinants of matrices with numbers. We're going to be taking determinants of matrices with mathematical functions in them. And to see why, I'm going to introduce what's called a Wronskian matrix. All right, so the plan is to use a determinant to establish whether or not a set of functions is linearly independent or dependent. And for that, we use a special determinant called a Wronskian. So let's suppose we have a set of functions and they each possess n-1 derivatives. Okay, well then the Wronskian of these functions is equal to the determinant of the following matrix. The first row of the matrix is actually just the functions themselves in a list. The second row of the matrix, so this would be the first derivative of f1, the first derivative of f2, the first derivative of f3, and so on, all the way to the first derivative of fn. Then the row below that will be the second derivative. And you keep going down until you get to the n minus 1th derivative. So that would be the first function, n minus 1th derivative of it, and the second function, n minus 1th derivative of it, and the third function, same thing, all the way down to the bottom right corner, which is the nth function at its n minus 1th derivative. So this thing is called the Wronskian of the set of functions. Okay, super cool. So we have this incredible fact, which is that if the Wronskian is non-zero for all the x values in an interval, then the set of functions is linearly independent. So if we have a set of functions and we're trying to determine whether that set of functions is linearly dependent or independent, it's a matter of working out the Wronskian for that set, meaning the determinant of the matrix consisting of this particular pattern. And if the Wronskian is non-zero for all x values under consideration, then yes, the functions are linearly independent. All right, let's check out some examples. All right, so here we have a set of 3 functions. And what we're going to do is build a Wronskian and see what we get. So the Wronskian of this trio of functions is equal to the determinant of the matrix formed by that pattern, right? So the first row is cosine of 2x, 1, and cosine squared of x. And then underneath each, we'll take their derivatives. So derivative of cosine is negative 2 sine of 2x. Derivative of 1 is 0. And here we get 2 cosine x times negative sine of x. You know, why don't we write this one as just negative sine of 2x? Since we know we have to take one more derivative, and this way we can avoid the product rule. All right, take one more derivative, and here we get negative 4 cosine of 2x. Derivative of 0 is still 0, and derivative of negative sine 2x is negative 2 cosine of 2x. Okay, so in order to take the determinant, we should probably paste the first 2 columns on the right next to this. So let me erase this guy, which is right where we want to be working. So we'll put the first column here. And the second column. Very good. We will now draw our 3 diagonals and our 3 anti-diagonals. So this guy here is cosine of 2x times 0 times, who cares? That first one is 0, right? Okay. This one here is 1 times negative sine 2x times negative 4 cosine 2x. So we're going to add in 4 sine 2x cosine of 2x. We're going to add in 0 again. And now for the anti-diagonals, we're going to be subtracting. So here we're going to subtract 0. And subtract another 0. And we're going to subtract the product of these things, which will be, we're subtracting positive 4 cosine of 2x sine 2x. And this determinant, in fact, identically evaluates to 0. So since the Wronskian of this set of functions equals 0, the functions are linearly dependent. Note that you may have predicted this at the beginning of the problem by recalling this particular identity. Since cosine squared is 1/2 of 1 plus 1/2 of cosine of 2x, then that means that if we subtracted cosine of squared, we would get 0. So we have constants -1, 1/2, and 1/2. That would produce 0 here. So it is evident just from that investigation that we would have had linear dependence. We have exponential growth and exponential decay. Let's see if they're dependent or independent. So I know, let's use a Wronskian. So we'll put in the top row each of the functions, and then right below them their derivatives. So because there are only two functions, we only need a 2×2 determinant. So we need the derivative of e to the x. Oh, I can't remember that, so we'll just put e to the x for now. And the derivative of e to the negative x, which we'll just go negative e to the negative x, and there we are. So this determinant of a 2×2 is significantly more straightforward. It's that product minus that product. So we're going to have e to the x times negative e to the negative x minus e to the x times e to the negative x. So this first product here is -1. The second product is +1. So -1 minus 1 is -2. So the Wronskian evaluates to the constant -2. -2 is not equal to 0 anywhere. Therefore, the set of functions e to the x and e to the negative x is a linearly independent set. This means that one of them can't be written as a multiple of the other. So it's not possible to write e to the negative x as, say, a constant times e to the x, which is probably a good thing, because if that were the case, then the definitions of sinh, cosh, and all those other guys would significantly reduce, right, from what they are, and you'd think someone probably would have noticed that by now. So this is a linearly independent set. Okay, it's time to tie everything together here. We've seen a lot in this lecture. So what do we know so far here? We know that if you have a set of solutions to a homogeneous linear differential equation, that a linear combination of those solutions will also be a solution. We also know that you only need to consider linearly independent solutions in this context. And the first thing we wrote down in this section, an nth order differential equation will possess n parameters. Okay, so how do we tie all this together? Well, it means if we write a solution like this, and we only have n parameters to sort of spend because it's an nth order differential equation, this means the solution to a homogeneous linear nth order differential equation will be of this form. It will have the n constants, each one next to a function, and those functions must be linearly independent. Each of these y1, y2, all the way up to yn, together, this is called the fundamental set of solutions on an interval. And when put together like this as a linear combination, this is called the general solution to that differential equation. Okay, let's write this down. So a set of n linearly independent solutions, say y1, y2, all the way up to yn, of a homogeneous linear nth order differential equation on an interval I is called a fundamental set of solutions on I. Moreover, the general solution to the differential equation is y equal a constant times the first solution, plus a constant times the second solution, all the way up to a constant times the nth solution. So when we eventually get to actually working out solutions to homogeneous linear nth order differential equations, we know the solution will have this form. And it's a matter of finding that set of linearly independent functions, each of which is a solution to the differential equation. So as an example, let me proffer that y equal e to the x and y equal e to the negative x. These are both solutions to this differential equation, y double prime minus y is equal to 0 on negative infinity to positive infinity. Okay, well, this is a second order homogeneous linear differential equation, which means that its fundamental set of solutions will have two linearly independent terms. Okay, well, we just established a few minutes ago that these are linearly independent terms. So that means they form the fundamental set. And as a consequence, the linear combination of those two guys is the general solution. Okay, the key is that the fundamental set has the same number of elements in it as the order of the homogeneous linear differential equation. That's how we can draw this conclusion. It'll never have more. If it has more, then one way or another you are breaching the linear independence of the set. And if it has fewer, like say we didn't have e to the negative x, then you just haven't finished looking for all of the fundamental solutions. So you can see that to solve something like this, we want to find the individual fundamental set of solutions, and then we put them together to get our general solution. Okay, so for our final example, we've basically got the whole game here. We are given a couple of particular solutions to this differential equation. We are asked to verify that they form a fundamental set of solutions, which comes with its own set of conditions. And once we've established that, we can then use them to form the general solution. So the first step would be actually to verify that they are indeed solutions, right? Which is the oldest skill in the book here. We've been doing that since section 1.1. So we're not going to do that here, but you of course could verify their solutions by taking their first and second derivatives and plugging them in and showing that the identity holds. So that would be technically the first step. But we're already told that they are solutions. So what are we going to do? Well, first thing we should do, which is very easy, is to verify that the quantity of solutions we're given matches the order. So here we have a second order differential equation, which means that its fundamental set should have two functions in it. And of course we are given two, so yes, that's easy to check. If we were given too many, either that means one of them is not actually a solution, in which case we'd throw it away, or one of them can be written as a linear combination of the other two, which means we wouldn't have a linearly independent set. If we had too few, it means we just need to go searching for another one using techniques we don't know yet. So the next thing to do is to verify that the functions are linearly independent. Okay, well, I guess we should use a Wronskian for that. And we are hoping to get anything besides 0. This will be a 2x2 Wronskian. So we have cosine of ln x and sine of ln x. Okay, we'll take the derivative of each. So that's negative sine of ln x all over x. and cosine of ln x all over x. So we're going to take this product and then subtract that product. So that first product will be cosine squared of ln x all over x, and we're going to subtract negative sine squared of ln x all over x. Okay, and what do we get? That whole numerator is just 1, so we get 1 over x. Is there any x value for which this equals 0? If there were a single x value on the interval we were interested in, for which this came out to 0, we would have linear dependence. But the interval, of course, is 0 to infinity. Even if it weren't, there's still no x value for which 1 over x is 0. So this is not 0 for all x specifically in the interval we care about, which is 0 to infinity. And therefore, this is a linearly independent set. Okay, so our conclusion is, since there's 2 of them, and it's a second order differential equation, and the set is linearly independent, we can conclude that the set forms the fundamental set of solutions. So we're not missing anything. We can therefore write the general solution, which was the last stage of this problem, to that differential equation as simply the linear combination of the functions from the set. So we could say that's a constant times cosine of ln of x plus another constant times sine of ln of x. And there we are. Note that this even includes the solution y equals 0. You just set the constants equal to 0, which we know is possessed by every homogeneous linear differential equation.